want to
Now
say
you're live.
thank you? Is that the first?
So it shows me the slide
Yeah.
that's coming up next.
Is it? Are you? Is this the first one? Okay,
Oh, there
that's
you
the
go. There's
first.
a title and everything.
Okay. Should we get the lights or no?
No, okay. That's what we'll see. What
Well, Lev, you should
yeah, I
introduce
have nothing much. Just to say that we're so happy to have Vinny here, and he is an undergraduate mathematician that is 3 years as third year.
Well, into the third year now.
Yeah, end of the third year as a PhD student in biology. Well, department
Ecology.
is well, ecology, evolution too, both. And his advisor is Stephen Cornell, is a mathematician, theoretical physicist that works in biology for a while, and it's at that school about 4 years. So he's just a year older at this department than the student. He's all student. Now he will work at the other university. I guess Began liked him and brought him in from Leeds to Liverpool. Is Liverpool higher up than Leeds, right?
Geographically?
in their reputation.
No.
I'm not actually entirely sure.
Yeah, but anyway, Began is a boss, and they probably act there like dictator. They could hire whatever they like.
As dictators.
Yeah, pretty much. They're heads of school. They're not elected chairs.
Oh.
They're like heads. They would step down someday, but that's not. Yeah. So
When
anyway, I
infinite
met
power is no
Stephen.
longer interesting.
He was like, obviously this. He is very mathematical. Reminds me of myself when I was young, and thinking you're doing biology with all these equations and evolving towards more biology with time. So
Okay.
Vinny will tell us about his dissertation. Right? That's basically going to be your dissertation.
Yeah.
We have pretzels here, and we have two kinds of beer in the refrigerator.
You start with the beer.
Okay.
Loosen up the.
All right.
Okay,
Well-
so this is a talk that I've given to the SMB and the European Society for Mathematical and Theoretical Biology. They had a joint conference in Nottingham in July this year, and the title of it is Anomalous Invasion Speeds in Highly Polymorphic Populations. So a little bit of background on the biological invasions themselves. So the Watts of Fisher and Skellum, they were some of the early pioneers in sort of developing mathematical techniques for finding invasion speeds. So some of the original work was able to give a speed for the invasion based on the reproductive capability and the dispersal capability. But since then, things have moved on a little bit, and there's now other sort of factors which can contribute to this speed, such as allele effects, environmental heterogeneity. So if you think in metapopulation type scenarios, and one of the more surprising ones is your choice of dispersal modeling. So depending on sort of what, say if you go for a dispersal kernel, which type of kernel you use can impact the speed at the end. So
Do you think that's artifactual or real?
Well, it can depend. I mean, it's one of those things that sort of it's really based on what your problem is. What type of dispersal do you think can happen? Sort of. So it's one of these things you would select beforehand.
Okay.
Rather than sort of.
It sounds like you think it's real.
So generally, I would use sort of Gaussian kernel, just diffusion. It seems to. There's some people seem to think it does a great job regardless of how simple it is, but that's exactly what we'll be looking at. So more specifically, what I examine is how polymorphism influences invasion speed, because it's largely an unknown sort of factor. Current studies often assume that it's a monomorphic population. So if you just have one population, this is the entirety of it, and here's the sort of the physiological parameters that give you your dispersal speed. So, for example, in the Fisher equation, you would have one R value for reproduction and one D value for dispersal. But this is often not the case. To think of an extreme type of polymorphism, you get winged dimorphism within particular types of crickets. So you have a winged morph and a wingless morph. So can you say that these two different phenotypes can be judged as the same? Is it an average you could take and say, okay, so on average they move this? Or does the flight morph contribute more than, say, the reproductive morph that doesn't move? So that's the kind of thing that we'll be sort of looking at, and how it actually affects invasion speed. So my supervisor, Stephen, and his previous student, Liz, had found that a dimorphic population can exhibit an anomalous invasion speed, which is just an invasion speed that moves faster than any in isolation. So if you have, say, here, this is for the greater reproducer, and this is for the greatest dispersal. So this population contains both a reproductive morph and a dispersal morph. So this is the speed they move at when they invade in isolation, and this is when they invade together. So you can see the disperser moves slightly behind the reproducer in this model, but when you bring them together, they move faster than either.
And both. Faster than both.
Yeah.
So disperser is the winged and establisher is the
Yeah, so that's for a dimorphic.
And what I'm confused by the fact that there are three. Why are there three?
So it's all under the same landscape, and on the y-axis here we have the density of the population. So each individual sort of line here is just a time snapshot.
So we see 2 time shots to see 3 lines on one graph.
2 delta T's.
2 delta T's.
Yeah.
Yeah.
So it's just to show that they're traveling wave solutions and that they move at constant speed.
Right.
So in this top graph here, we have only the establisher morph in isolation. Here we have only the disperser in isolation, and here's the combined when the two are in population together. So here sort of is their equilibrium point at 0.5. So that
in equilibrium point, you mean the inoculation point?
No, so like the equilibrium for the population. So they're carrying capacity.
Okay.
Is a better way. So as you see here, it's 1 because they're only in isolation, but here it's 0.5 because there's 2. So they had found that these dimorphic populations can exhibit anomalous invasion speeds.
Does anybody understand that last graph?
What are on the variables? What are the variables on those? 0 to 1. What is the 0 to 1?
This is the population density. So this
on the
is
vertical.
yes. So
But these were 1.
Density of-
Everybody was 1. And then it moved kind of in time.
Oh.
And
So this is
was
density of the 2 morphs, you mean?
yeah,
Relative density of the 2 morphs.
relative density of 2 morphs.
Ah,
Yeah.
okay.
with the whole entire population.
Okay.
Yeah.
So that's the starting.
So you start the population half dispersers,
Half reproducers, yeah.
Half
So they
reproducers,
both
they
have,
all-
yeah. So you
Yeah.
have a position in the landscape,
okay.
and it just you
Half
say,
of them are this and half of them are that.
yeah,
And altogether, they will go, this much by density and this much by dispersal. And they will go overall double or something, whatever. Both movements will happen.
yeah.
I'm thinking. So this is Elliott et al.'s graph, right?
Yeah.
So we can trash this if we want. But I'm thinking that all we should look at are those 3 vertical lines, right? And ignore those.
Yeah, that's
slope lines.
just how the density is
Right.
approaching.
Okay. So if we have those 3 vertical lines, exclude those, or take just those in that last graph and compare them to the previous 2 graphs. That's what we should be looking at.
That's what
Yeah.
And then there's some other wrinkle about the relative abundance of the 2
Yeah.
Yeah,
morphs.
but 3 vertical lines are ahead of each of the 2.
Yeah, ahead of the prior,
Okay.
And why,
or not prior, but the other.
Right, but the 2,
I'm confused by this. It looks like the disperser
Goes less.
starts off not as far out along in the,
They all start off at the same point.
but just what you didn't. Well, you start this
Apparently, establishment is part of the story.
Yeah, so the establisher here just gives you a faster Fisher speed when you combine the two.
They disperse there, but then they don't reproduce. So it's maybe that's what they're counting.
Okay.
So
That's it. Come. We have space.
So
Okay.
this is just a little sort of part to sort of talk about the anomalous
So the
invasion.
mixture invades faster than anyone in isolation.
Yes.
So the mixture invades.
Yeah, that was the key
Population in a
finding.
mixture.
Yeah. So
And what happens? I mean, these two morphs obviously interbreed with each other. They're part of the same species, and any individual can give rise through reproduction to a morph of either type, right?
so this is an asexual model.
It's asexual. Just
Oh,
simply
okay.
50% of one
Yeah.
type and 50% of another. They're not breeding.
There's
I mean,
a,
not with each other.
Yeah.
They're like asexual.
They're not breeding,
Sorry,
and they can't produce either type. They produce only the same type that they were.
no, there is a proportion which mutate at birth
Ah, there we go.
into the other.
And is it
So it's-
50-50 or what is it?
Well, for these ones, I think it was set for the numerical simulations anyway. It was set at 0.001.
Okay.
So it's not that the establishers have to prepare the ground for the. There isn't actually any cooperation or facilitation between the two. It's simply
No, this is actually a non-cooperative system.
But it has to work by that mutation, right?
Yeah,
They have to be
mutation's
able.
key.
They have to give rise to either morph, otherwise it wouldn't
So
change.
if you started the population off with 100% disperser, but with mutation,
Yeah,
we would see. the same thing.
asymptotically, yeah, you would eventually see.
Some of them.
Yeah.
Right.
So
That's a simple non-interactive thing. And now you're going to switch to diploid case, right?
we'll be looking at diploid later. This is
So if you
sort of,
say homozygous, heterozygous, those are
Yeah.
diploid concepts.
yes. So this was a study done by Weinberger et al., which had shown that homozygotes can spread faster in the presence of heterozygotes than either in isolation. It's just another example of an anomalous invasion speed occurring. However, this was only in a strongly cooperative system, which
Or the homo and the heterozygous ones cooperate with each other.
yeah. So there's a cooperative effect, yeah. So there's some benefit of either the homozygote and heterozygotes benefit one another. So it's been known and proven mathematically that this can be true in cooperative systems.
Can you give us an example of, I mean, just malaria resistance like that? Or where do you find cooperative systems across the zygos or the heterozygosity?
Yeah, cooperative means heterozygotes are superior or something, or better off in reproduction.
That's not what he said.
So
Is that example of cooperative when heterozygotes are present? That is example of
Yeah.
cooperation of two alleles or something.
yes. So
It's,
to get the actual exact
Wednesday,
thing, I would actually have to read
Wednesday?
the paper. But
today's Monday. No,
read the
today's
paper
Friday.
again.
Sorry, Monday.
I can't quite
Monday,
remember the details
Monday.
off the top of my head. But it is down here, in the sort of bottom right corner. I can sort of explain it. I need to read over it again to get the final details. But the important point for the Elliott and Cornell paper is that it was a non-cooperative system. So there's no cooperation at all between these phenotypes, and these anomalous invasive species were shown to exist. And there's currently from speaking with a group in Swansea, they've shown that this linear determinacy for the spread speed is the exact speed for this system. So in this paper and in our calculations, we couldn't show rigorously that the invasion speeds that were calculated were what the system should travel at.
Mhm.
But this has been shown for two anyway. But anyway, so our aims were to look at the example when you no longer have just two phenotypes in the population, you have n phenotypes in the population. So it exists for two, but what happens when you include more? So say 3, 4, n, anything you want. So what
Shall we take bets? I say bigger and faster. faster speed.
Okay, noted.
No takers on my bet.
I say it's a limit to the speed when n is higher. It's not going to be faster than something. Okay.
So 2 is the fastest.
No, something may be faster, but not too fast. And it's stop when n increases.
Oh, sure.
It will be asymptotic to something. Okay. All right.
Okay.
So
Our
we
bets are
just
placed.
extend this previous model that they use, which I'll show very soon. We just extend this to the PDE model just to include more moss. And we want to know, do we still see the anomalous invasion speeds, or do we see something else? So here's some notes about the population.
Haploid population.
Yeah. So we use a haploid population. It's polymorphic at one locus, and each genotype is expressed as a distinct phenotype. So there's no epistatic effects within the model. So if you have one particular genotype, it expresses one particular phenotype. There's nothing more complicated than that at this stage. So each phenotype differs in its dispersal, reproductive, and competitive abilities. They can. So they reproduce asexually, and a constant proportion mutate at birth from the parent genotype to the other genotypes. Now, this, for the results I'm going to show here, this isn't sort of nearest neighbor mutation. If you are in, say, phenotype 1, you can mutate from phenotypes 2 to 10, which can have a
Equally.
Yeah, equally
Full
available.
matrix, equal.
Yeah. We're currently working on the nearest neighbor. So if you're 1, you can only move ever so slightly, because that would be more realistic. You can't become a reproducer and then suddenly your offspring becomes a great disperser. So it's to try and include the realism. And from the simulations, it looks promising that the same behavior we find in this model carries over. So, sorry.
So you said you can't. So parents that are not great dispersers can't produce an offspring that is a great disperser.
In
could.
this one, yeah.
In this case, they could.
They can't.
Everyone produce everyone with equal.
That's
Yeah.
okay. I'm
That's
sorry.
the code.
I heard the opposite.
Everyone produces
Thanks.
everyone. You
Yeah.
take and everyone else. The whole matrix is equal.
Yes.
Okay.
So this is just like a quick talk about the landscape that we use. So we used a homogeneous infinite landscape that was continuous in space. Time was also homogeneous and continuous, so we had overlapping sort of generations. There was no generational time here. And
space is a line.
yeah, space is just one dimension. So for our model, we didn't have anything, any particular dispersal capabilities that if you had to change this to 2D, it would be the same, except it would just be a radial sort of dispersal. So we just use one
Radial
dimension.
dispersal in 2D.
Yeah.
That's what he will show to Nick, because Nick said you need to do the 2D version.
Already go.
You already got it?
Yeah.
Okay.
That's skeletal.
So you're going to go to 2D.
Yeah. So provided there's no sort of heterogeneity in the landscape, this result would carry over to higher dimensions. But for the purpose of for our research, we just want to do it in 1D. So we do assume traveling wave solutions. So here's your traveling wave variable and your x minus ct, as standard c being the speed of invasion, the speed of the wave. So here are the equations that we use. I'll take a bit of time to go through these. So
Cij is competition.
competition, yeah.
And what do we assume about those?
So for here, it's just a numerical value. And so the I and the J is just some competition factor between each.
Are they symmetric, Ij and Ji?
For this particular research we relax the condition and make competition neutral, but it doesn't have to be.
Or neutral make all the same number?
All the same, particularly for the numerical
Each one with
simulation.
each one?
Yeah.
Equally?
Yeah, equally compete. So that we're
Including
competition
itself.
neutral. Yeah.
So not just symmetric, just equal. Just all equal.
Yeah.
Ij for all Ij.
Yeah. You don't have to do that.
But ours are
yeah.
different.
If you
right?
really, if you really had an establisher, it would have maybe a higher
Yeah.
or something. Like
It's,
Yeah,
it's,
but ours are different, right?
Ours-
Yeah.
And these are different.
yeah.
These and ours are different.
Yes.
C's are the same, mu's are the same, as you said.
Yeah.
And, that's in and out.
Yeah.
In
So
and out.
they don't necessarily have to be. This is the general form.
Yeah, that's a general form, but at the moment, for your assumptions, you might
Yeah.
mu equals C.
Yeah.
Yeah,
So-
there is a lot, I'm just all sitting on the seas today, that's what I'm writing about in my
Yeah.
book, about this competition coefficients, which is, I'm not talking about equal, but all historical ones always assuming symmetry from Lotka-Volterra, which I don't know where, from physics,
Yeah.
action and
Probably,
counteraction or something, and that they got it, and lived till May until today. They were Matt Peake's, your teacher's papers a few years ago in the American Nationalist, which are smart papers generally about species.
You can get as many
All
species
keep,
as you want.
keep symmetric assumption. No reason to do it.
Yeah.
In biology, the symmetry of effect of one. In fact, it's opposite to this. We find a lot of examples of completely asymmetric, like pecking order competition, like a shading of plants. This one shade this one shade that, and of course this one shade. And it's so triangular matrices with zeros on one side and negative on the other side. That everywhere. So lots of
another
examples.
chapter.
Yeah, lots of examples of it. I'm writing about it now. I'm reading literature, finding examples. It's just amazing how some people call pecking order in species, like in birds eating, inside the population. They have examples of that. That's incredibly interesting. How different their biology is from what have been assumed with theoretical biology. Of course, May, using the symmetric one, discovered that
Robert
for
May,
coexistence of a lot
Robert
of species, you need the interactions to be very weak. That's the only way you coexist. Because
Well,
diagonal is negative. That's a
But not if they're
They're
asymmetric.
But if they are symmetric, you don't have to.
Sure.
If there are zeros on the other side, triangular matrix is stable by definition. You read the arguments on diagonal.
Right.
As long as you have self-damping terms, you're stable.
Right.
With any strength of interaction, as long as it's asymmetric. And that is, I say, why we have such a common pecking order in behavior too. I think it's such a stable structure to be, uneven and unequal and asymmetric. This guy dominates everybody. The next one dominates everybody but one, and so on. And that was not, I'm just rambling about the wrong assumption in ecology.
Do you suspect that the
About
asymmetric competition is going to change the result?
No,
Well-
the constancy. I'm
Well,
not sure.
I'll show you a minute because
Anyway,
I didn't assume that this was constant when I first done these calculations.
Yeah,
Oh,
but
okay.
I'm just sitting on it now, very much so. So
He may have something to say.
So
about
make something to say. If we get to it, I'm very interested in what happens.
Okay.
A mutation, you want to make them more like neighbors. right?
Yeah. That we're
Everything-
working on that
everything
just
to
now.
everything.
So
In
when
order of things.
you do the calculation, it doesn't actually make a difference because when you see when I come to the part which talks about how I got the result, you'll see that it doesn't really make too big a difference. So here's just a dispersal. Here's your diffusion constant. Your Lotka-Volterra growth terms and
Yeah.
competition terms are here.
So how about CII? What is on the diagonal there?
CII
Ones.
can be 1.
You could put ones there.
Yeah, you could have, but as I said, when I done this calculation analytically at first, I never assumed anything about C.
So there are the differences are in R's.
Yeah,
Okay,
R's
so you know.
and D's for the numerical simulations. Okay, so yeah, so this is just notation here where S is just a set of all phenotypes within the population.
I'm sorry, what? What's the slash?
Oh, the slash here means the set excluding
Excluding its
Oh,
own.
okay,
So
so it can't
mutation
mutate into
from
itself.
somewhere to somewhere.
Okay.
Okay, happy to move on.
Okay.
Okay, so the technique we use to find what this invasion speed is from propagation into unstable states. So the benefits are, well, generally you can't sort of to sort of break the PD down into a system of ODEs. You need to know what the speed is, which was what we didn't know. We couldn't estimate. But using this technique, we can tell long-term asymptotic behavior, and the asymptotic behavior we want to know is the speed, the invasion speed. So basically how it works is that small perturbations grow and they spread. And the behavior at the fronts are inherently nonlinear, just like our equations. And this is a paper by Vansalos, which is, if you want to print it off, it's about 300 pages. It's huge.
But this is completely not Skellum, right? I mean, this
No,
is
it's a different technique.
absolutely different from Skellum.
It's a common technique. It's used. It's just that the most recent version that I used was by Vansalos. So just a quick overview of what it actually does. You formulate it from the Fourier transform of the initial conditions, and then you take a saddle point approximation around this K star, which is the wave number. It's a critical wave number, which links certain parts of the solution together. For example, it's this K star here and here, which give us the relation to the speed. But this is sort of under the bonnet stuff. The only relation we actually use is this main one here. So this is where omega k here is the dispersion relation and k is the wave number. So we just use the derivative of the dispersion relation with respect to the wave number evaluated at this critical point, which gives us the imaginary part of both.
This is like Fourier transform of something or other?
Yeah, the initial conditions.
Of the initial condition.
Yeah, so there's you take your ansatz. So here you can see
Phi of k is the initial.
Yes, if I remember.
And you're solving
right,
for the
K is what
speed, right?
It's just a variable, but
K is the wave number.
Wave number distribution of the Fourier.
Yeah.
So, okay. And this is a Fourier image with this say.
Yeah. So I think this is the inverse one actually. If I remember.
I kind of missed why we need to do this so generally, because
Go from PDE to ODE.
Linear. No, it's not linear equation, but you linearize them.
Yeah, so that's what comes next. But this is just
it's not linear equation. You have logistic there
Mhm.
in competition. But in order to use Fourier, you have
but
to apply
is C
to
going to be
linear
constant?
yeah,
C is the
that's
speed, right?
Yeah, Fourier
Is-
is applied to linear equations.
Yeah.
So you need to first linearize them.
Exactly. So this is sort of when I gave this was a background so most people in the room knew this technique, so I didn't have to go into much detail. But
Mhm.
it was just to show that this thing here is the important part that we use to get the speed. But this is just where it comes from, why it's valid to use it. But again, we do linearize the equations, which is sort of the next part. So
let's start with that. Okay, so
Yeah.
you have
So we examine two equilibrium points of greatest interest, which is the coexistence and the trivial sort of
Absence.
extinction, absence. But we linearize around the unstable state, the zero, and we get this relation. Now the important point to remember about this is competition falls out. There's no competition, has no impact in the linearized version of these equations.
zero.
Yeah.
Not around zero.
Because that quadratic means around zero, then dropping out.
Yeah. So here's just a change of variables here, so we can take the R tilde also has your whichever phenotype you are plus the sum of all the mutation into that term. So it's just a case of this, not a big deal. But as you see here, this system's now all positive. There's no sort of
Zero is
non-cooperative.
unstable.
Yeah. So if you move ever so slightly, then the exponential growth brings it up. So that's why it's unstable. But as you see, that it's no longer non-cooperative; it's become cooperative. So you can see the NJs here. These are all the other phenotypes. So you can see it's went from a non-cooperative system to a cooperative system once you linearize, which has important implications for us when we try and
I don't know.
determine the speed.
What does that mean?
Well,
What does it mean to
cooperative
be
means
cooperative?
one end helps the other end
Yeah.
to grow. This is linear, but it helps.
Yeah.
It's not non-linear, it's linear, but it's from around zero.
Yeah.
But Ij is positive, all the mu's are positive,
Yeah.
all the mu's. So if one end increases, the other end gets a plus from that.
Why
So
should
he call it cooperative. If they are independent, then it calls not cooperative. If they don't know about the other ends.
Yeah.
If one end does know about the others, he calls them non.
So what's the biology behind that cooperation?
Mutation. In this case, from zero, because everybody mutates in anybody to anybody. Then they look cooperative around zero.
because I could
Some
come in,
densities are
Yeah,
low
you
enough.
come
I
in.
could come in as a
from this
winged
to
morph,
that,
but I
from that to that, and
increase the
around
established
zero,
morph.
they all come in anyway.
Okay, that makes sense.
Okay, so that's our linearization. So what we've done next was we just changed this linearized problem into an eigenvalue problem. We substitute in this ansatz function. So where this iota is just to describe the phenotype, so we don't get confused with i's and complex i's.
So it's L now for the number.
Yeah,
Mhm.
yeah. It's just for this one slide, just so we don't get confused by the by I being the complex
Imaginary
variable.
union.
So to do the calculation, what I'd done was I made a change of variables. So made this lambda q the imaginary part of the dispersion relation, and this k term became the imaginary. This IQ is the imaginary part of the wave number, just so I could get rid of the complex algebra, and then q and lambda q are both real. So that just makes the calculations easier, but it's still equivalent enough. So we changed these linear equations and we put them into this matrix. And you can see all the off diagonals here are mu. So we made a simplifying assumption that all the mu terms, all the mutation terms, were equal. We made that assumption just to make the calculations simpler, really. So all we have is this diagonal term. So now, if there's no mutation, you can see that you just have these diagonal terms, and these are your eigenvalues that fall down. But it's not quite as simple when it's larger, and these are well, it's simple enough when mutation is 0, but when mutation isn't 0, this isn't quite as simple. But you can solve this matrix equation to find your eigenvalues. But we basically have to make the determinant of this 0. So what we can tell is for this actually to be 0, one of these diagonal terms has to be 0 or close to 0 when mu is small. So you can see here, if this is small, because we make the assumption that mu is small, your chance of mutation is going to be small. And it's squared, so it's going to be even smaller. So we have at least one of these members in the product must also be that size too, must also be small. But what we do is we examine a behavior when the mutation goes to 0. We set that limit. So to calculate the invasion speeds, after lots and lots of algebra, we come to these two relations for the speed. We get 2. So we have the case, just as the sort of FKPP equation, just as it was found by Fisher, etc. It's the same. That this is a monomorphic case, so you would expect that each in isolation gives you this. But here's what happens in the polymorphic case. These L's are constant. They're just a choice of which phenotype you use. As you can see, that no matter how big your population is, how many phenotypes are in it.
What's L and M? All possible pairs.
So it is possible pairs. So
L and M, but then this is like, what do you know, minimum of that or maximum?
So, well, this was actually a difficult thing. We tried to find exactly which speed it was. But the important point of the result was that when you had n phenotypes, the speed of invasion was only determined by at most 2 phenotypes within the population.
By some 2.
By some
pair.
Some pair was dictated the speed.
We don't know which one, but
So I lost my bet.
Yeah.
one of the pairs will be.
Well, we come to that for ways in which we can sort of determine this. But yeah,
then the R's get close, and that means you have a very high.
Yeah.
The denominator is close to 0. So
yeah.
You get a very high speed.
So there are conditions which come out which pairs can be used. There are particular conditions. So when we found these solutions, they were valid in the limit as mu approached 0. However, what we wanted to know if it was biologically relevant was we had to make sure that on the approach, as mu was converging to 0, that we still had consistency within the solution. So biologically relevant, we couldn't have any oscillations in the population, because if they started oscillating close to 0, you get a negative population in your result.
I hate when that happens.
Doesn't make sense. So we wanted to check that this didn't happen, and it's just a case of we'd taken there's a particular q squared value. If you remember, it's a wave number. If you just add this correction term, so it's a perturbative approach where we just sort of, here's what our limit was, but we added a small term that was dependent on mu, which also had this behavior of mu converging to 0. But if you substitute this,
So it sounds like a fix. It's not. It's. Am I the only one who feels that?
Well, it's a way to get mu into Q.
So you could get, how can you get these two together? RL or RM is kind of big enough for this two to get them two. But that would be very different, the difference in R and Ds, right?
yeah. So the R&Ds are by approximately
Should be.
about factor 2.
Should be flip-flop, like,
Yeah,
in order to have both of them greater than 2.
yeah. It really
You mean
restricts.
that I need to be extremely
Yeah.
different in R and different in
Yeah, that was a condition.
and the
that
other
came in.
way around.
Yeah. So
And under this condition, what happens is anomalous speed.
yeah.
Very high speed.
So yeah, exactly. But again, this is just a case of
Yeah, it looks to me like a generalization of something very classic. I mean, we have classic in biology, right? Larry Slobodkin, you should know better, Scott. About Larry's, his name is related to, he was second with somebody famous on this inequality, on red tide. Red condition for explosion of, so basically the question was how the red tide appeared in the, and the inequality is this R and square root of D or something. I can't remember the first one, the simplest one. For a symbol, before you went polymorphic, what was that? R. There was some sort of
square root of dr.
square root of dr, but I can't remember. If you look at the name Slobodkin, somebody first before Slobodkin.
But his early red tide paper.
The red tide paper. Yeah, it's a second and
There are
famous.
multiple morphs in the red tide.
No, one. But the question was, you have exponential reproduction of the just population and dispersion. Now, if you reproduce with some rate and disperse, you never get any kind of red tide because they reproduce and they go away fast enough, and the density of cells is so low that it looks like water to you, because every new reproduction and dispersion takes it away. So a simple diffusion equation with R. It's simple. There's no mutation. This equation that you have.
Yeah.
This fusion with D and R, and no logistic. No, it's from zero. It's linearized.
yeah.
Don't even
No
bother
logistic.
with
It's from
logistic.
zero, right? So we don't discuss the nonlinearity. It's an linear or around zero. And then, if you reproduce so fast that
You can't disperse away fast enough.
Disperse away fast enough. You disperse, but too slow for that R. That's exponential. The R is exponential, but D doesn't take it away. What you get is you get a red tide.
Blue.
You get the whole sea looks red or whatever because of this bacteria. They reproduce so fast that dispersal doesn't do it. That was a simple inequality for either having a red tide or not having a red tide. And it was relating this to in this equation, fusion with R. And then just a simple inequality. If we look at
That'd be a
online,
lovely connection.
yeah, you need to. That is the famous, it's called the red tide paper in this classic in ecology. Totally classic. I mean, I think only second to his
Is the Earth green?
for the why the world is green paper. Why the world is green is his number one because it's wrong. It's
Must be a
number one.
primary color ecologist.
Yeah, he's like he's like totally famous for that.
Green
for
is
that.
secondary.
Why the world is green? That's about the trophic levels paper.
Yeah.
And the second, why the world is green. But this is about herbivores and herbivores. Why the world is green? Why there's vegetation?
Why there's
left?
vegetation left?
Why vegetation left at the fall? Why couldn't they eat it all? Why didn't they evolve to finish it off by fall? Right?
Yeah.
Because it's going to come again in the spring. What's the hell? Evolution should take care and eat the food, right? But it doesn't. Every time we have vegetation left, every fall. And so his explanation was that predator attacking birds, whatever, attacking insects enough, don't let them eat the food. If there were no birds, the assumption of this paper is there was no bird, just insects, would have all the green eaten by the fall. The wood. It is just, it's not eaten because of the bird. I don't think so.
That's not related to this.
Yeah, but anyway, that's the first paper.
Most
Let's
of
just
that
explain the other
huge
color.
And that's
people
the
want
huge
ligand.
paper, huge citations, and all textbooks and everything.
Right.
And second, in citation, also quite noticeable.
And that's what made him famous,
That's
actually.
what he made, that young. He was very young. It was his first job after college,
Right.
You got help
working
from
for the red tide.
You got help from Okubo, right?
Yeah, Okuba worked on this. Okuba has literature on it. Yeah, Okuba, Akira Okuba.
Not at the time.
No, later. He
Yeah.
worked on this differential equations, partial.
Yeah.
Yeah, and it looks like you don't, your teacher doesn't know about this literature. That is very relevant because that biologically important phenomenon in it was also explosive. The phenomenon is that you either do or you don't have these tides, color tides. We have them here in Long Island, we have them around the world from time to time. Nobody understands, but the best explanation is the relation between R and diffusion.
Yeah.
There's a certain relation, you're going to see the sea going red. Or whatever color, different place. We have some other color in Long Island. So, in around Hamptons, we have some color. Whatever it's famous.
Brown tides.
Brown tides is called. Yeah, brown tides. We have brown tides here. What are different bacteria?
Different
Different bacterium. The different bacterium is brown, and some of them are red. And I was just always thinking about that because I remember that's come from the same equation. It was without competition. It was just linear. And the question is which outrun what, diffusion or R. And if it doesn't, the density goes to infinity, so to speak, because there's no logistics. So density in this point, density of cells goes, linear equation doesn't know that it stops. There would be a density dependence.
I mean, a red tide or a bloom, an algal bloom, is an invasion of sorts.
It's an invasion, but it's invasion.
But
Invasion
so-
of sorts, but at a given point, it goes like mathematically to
Yeah.
infinity because
Right.
they didn't have it in this equation.
So Vinny's conditions are slightly different because of these polymorphic.
But he has
of these
more than
morphs.
one, and he has. But the red tide also has. Red tide also had a rate of spread as well. I mean, red tide existence depended on R and D relation, R dispersal and R relation, whether they will exist or not. But I think they computed the way how fast.
Yeah,
I think
you should be able to.
they should be able to. And then, what you are saying is that with multiple morphs. I mean,
And it's multiple morphs, and it's also across space,
across space.
which makes it different too.
Yeah, across space.
We talked really briefly here about how, I think about when people use in these models, a lot of times will assume a trade-off between little r and d.
Yeah, okay.
Right?
This
Are you
also
coming up to that?
Yeah.
It's almost like you'd be at the wavefront. You're selecting for a population consisting of things with very different r's and d's.
Yeah.
It would look like there's a trade-off, right?
Yeah.
But it's actually
So this is sort of this work. So when we first came up, when we first finished these results, we presented it at the conference. We were ready to submit to Theoretical Biology, the journal, but then it was taken up with such sort of fervor. Everybody sort of thought this is incredible, and then we decided, okay, we'll push for somewhere higher, but the higher impact journals require a bit more. So we are working on the trade-off stuff and the nearest neighbor stuff, so it's more palatable for the
Because
left.
it's more powerful for biology.
Yeah.
To
So it's
see
more
that.
relevant.
More biologically
Mhm.
meaningful. We're
Yeah.
looking at mutations along the diagonal kind of,
Yeah.
along kind of a trophic chain.
Yeah.
Along the diagonal, not all the matrix.
Yeah.
Okay.
And
Uh-huh.
so that's sort of, we're still working on that just now because we were trying to
Well, you
finish.
could work on it. You could still publish that in a lesser journal.
Yeah.
Theoretical and work on the better thing. Don't delay. Publications take such a long time.
Yeah.
My advice to students is rush to publish whatever you
And there is no republication scandal. Publish the same thing many
publish,
times.
and then when you get a better, meaningful result, go in a better journal. But in the meantime, publish that. I don't delay publication. It has very.
Yeah. Because it's drafted. It just needs improved.
But I think we need to look back to Okubo and to whoever and Slovakian implements.
Are we at the end? We're not at the end.
No.
let him
let's
proceed.
go.
It's like drag.
Yeah, for
Drag.
Christ's
No,
sake.
no.
Where's the paper?
Anyway, real good. So
Okay. So once you substitute this in, this is just a perturbation that's dependent on mu. After you do it, after some lots of headache algebra, these two relations fall out, and they must both be simultaneously satisfied. Otherwise, anomalous invasion speeds don't exist. And it sort of comes down to a condition on the population size, or is it the population size? It's back. One of these diagonals, all it has to be positive, but to satisfy the condition, this can't be negative. and that's one of, or not sorry, negative, complex. It cannot be complex, and that is why these sort of relations fall out.
Can you go back to the condition? Sorry.
Oh yeah, sorry. You?
It's L over M, and then M over. Okay.
Yeah. So if you have the L and the M just denote some pair. So if you select an L, say it's 1, you have say 2 to N to choose for the M. But it's not just a case of a choice, as we'll come and see.
Is that true for each pair? No.
It has to be true for each pair. Yeah, this condition has to be satisfied for each pair.
So that is basically in words means that the very good high R guys have to be low D guys.
Right.
Yeah, there has to be a
So it's like
So if you had random combinations of R and D chosen from distributions, you threw them all together, the things that would be
at the front.
Wait a little while, and right here you get a bunch of things with high R, low D, and high D, low R. Right? It'd be this selective. It start dropping out of the population. The fastest moving combo is that pair.
Yeah, but the interesting part is it's the exact same result that Stephen and Liz found. It's the exact same thing. It's just which was quite remarkable.
Stephen and Elliot and Cornell.
Yeah, Elliot and Cornell. Sorry, not being formal. But the remarkable thing is that the speed doesn't actually depend on mu. You would think that higher mutation, if you were mutating the mutation was high, you would have more coming in the front, but it doesn't.
That will change when you ditch the nearest. If you go to nearest neighbor or small increment. I mean, it'll be a waiting. You wait until you achieve the largest possible difference.
Yeah.
And then you'll hit the largest speed.
Yeah.
But because everybody is equally accessible.
Yeah.
You immediately get this combination no matter what.
So we've run some simulations. It's a bit hard because you have to run them longer because the behavior's slower. But essentially, there's no speed up from the mu at all. It's just when mu is vanishingly small, it exists. I mean, if you have 0 mutation, you just get the regular Fisher behavior. If you have the tiniest amount of mutation, this anomalous behavior the system can exhibit this anomalous behavior. So this is the parameter space of our condition, or the two conditions here in the bottom right. So in this region, if you fall in here, you'll travel. Now this isn't the best example for it, but I think this is the establisher. You'll travel at the speed of the greatest speed that the establisher can give in the Fisher relation. And the same here is true, except if you would fall and you would travel at the speed of the disperser. However, if these conditions here are satisfied, which is this sort of hatch region here, you will travel at an anomalous invasion speed. So this is a parameter space, or well, the ratio of dispersal over the ratio, or the reciprocal of the ratio of the dispersal.
You don't really mean anomalous. I mean, you actually mean fast, right?
You mean as fast
It
as
can never be slower. It could be anomalously slow, and you never get that.
Anomalously fast.
Yeah.
Right.
So it will travel faster than in isolation. It's essentially what we're seeing here. Not slower.
It's imprecise to say anomalous. You know more.
You need to say high.
Yeah, fast.
Fast.
Okay.
So, is this geometry especially interesting, or?
Oh, it's just a region of where these speeds are possible. So you've got this little one down here, and then this bigger region.
Based on this two ratios.
Yeah. So
as axes.
Yeah.
Based on two ratios as axes.
So yeah. So if you need to sort of differ approximately by a factor of about 2 for this to happen, which says they've got to be quite far apart. Just as Nick was saying, like, if you have this trade-off, yeah. So this was just a reiteration of the speed again, and it was dependent on at most 2 constituent phenotypes, and we referred to them as vanguard phenotypes because we find in very low densities at the front of the expansion, these two phenotypes are at the front.
Well, Nick has very clearly explained it, right? That
You actually do find it
watch the
empirically?
wave.
Not empirical.
Oh, okay.
If you watch the wave for a long time, you'd see those two at the end.
Yeah.
If you watch the wave going, at the end you'd see them selected.
Yeah.
There will be majority there.
There should be evidence for. I mean, this should be clearly evident in real data somewhere if it's true.
Well, what I think people have been citing what looks like functional trade-offs between dispersal and reproduction. I can devote more to my egg production because I don't need energy for to
That's how they
dispersal.
say
That's the
it.
Just So story.
Right.
That's the story. This
So
what
there
he
are
says is
plenty
really
of-
true.
Right,
Well,
I
Whereas
understand.
what biologists
So
say
is there
maybe
empirical?
made
Is
up
there
story.
empirical observation that
Let's say that
corroborates?
if you put energy to
There are
one,
two, exactly
you don't
two
have enough of
morphotypes?
the other, and but this is
Because I've never heard
The
this
the
before.
best example is in bugs. We have winged and wingless, and plants. Plants have seeds that do not attach at all, and seeds that do.
Really?
Different size seeds that are more or less capable of wind dispersion. And I think there are probably examples of things that have produced more of a continuous distribution of
Well, maples don't do this, right?
right. Well, I don't know. There might be a fraction
Conifers-
of maple
conifers
seeds
don't
that,
do
that
this.
don't close, right? That stay
Oh.
on the branch.
Is there a
say
story,
the French law.
Emily, of dispersal versus reproduction, kind of like a dichotomy? Either you are good disperser or you're good reproducer.
And that you need both at the frontier.
Oh.
You meet both of them at
I've
the
never-
frontier.
I've never-
There's
I've
one where
stu-
you need
I've-
both.
I've
No,
thought
you
of-
meet both, what he says. at
Yeah.
the frontier.
I've been reading invasion stories for a decade. I've never heard anything like this.
The aliens land. Things can go quickly, go wrong.
There are big fat ones and there are skinny fast ones.
What about like mammals that only have like one or two offspring, but they can migrate really far? Does that count?
Well, it counts if there are two kinds of such mammals.
No, but he says that it's two that would be present, right, in the front wave. That we observe the front wave, we're going to find a slow disperser that's high reproducer and a high disperser, slow reproducer.
Yes.
We'll find them together there. Is that what we
Yeah. At
we'll
low
find
density.
a mixture of the two.
Yeah.
Out
At low
of N
density.
forms, out of N haploid forms, and the observing this,
Yeah.
find two. Let them think about that. Is that if we found one of the two, then it would be a totally explaining what biologists make up as a as a trade-off of energy or something, which is nothing to do with it or whatever. But we have find two. Maybe that is what they say, that we find plants. What can't we think the front of the wave is what we see now after a long time of selection?
Well, no, see, that's the,
No.
if you have, it's
No,
very
it's
interesting to
invasions.
let the population dynamics run out after you've filled, if put an end to linear space, right? So it's an island or whatever,
Yeah.
and it fills, and what comes in the middle, now you no longer need that pairing. That pairing is no longer essential. So,
Right.
so you should eventually break up this negative association between the two rates.
Yeah. It's remember it's linearized at the unstable
Zero,
equilibrium.
At the zero. At the,
Yeah,
Right, so it's
at the
completely
wave, that's
wrong
stable.
for
It's
it to
like
carry
the Hawkins issue, only with
Yeah,
form.
yeah.
Yeah, it's an issue of spreading out of
Well, maybe it has
very low
military
fi-
applications.
very low. No, yeah.
No, I'm serious. No, I'm serious. Right? If you want to, you want paratroopers, and you also want the ground force that will keep this land now that you've got it. Right?
So you have to be able to have the two types of soldiers.
Yeah.
Dispersers and
Yeah.
folders.
Paratrooper would turn into a foot soldier and vice versa.
Or the guy
Sure.
who carries a really heavy but powerful machine gun paired with dudes with
Nice.
light arms. Long
Long
fingernails.
fingernails.
Or what about business?
Well, let's think
Yeah,
about it.
competing
It's
businesses.
interesting because,
I don't know if you'd have mutation there.
well, my question is how to interpret it interestingly for biologists because they do have, I'm sure they have a story that either you're a disperser or a producer, and they justify it nothing like this. They justify it by like a evolutionary strategy.
Oh, of course.
Distributing the energy one way or another. But if you have exponential,
We have the
right?
Lancôme's thing. Remember the Lancôme Medical Center?
Yeah,
Bo Shopson says
yeah.
we genetically examine each of these diseases that have found them. We thought they were hospital transmissions, but we examine her contamination and her contamination, and we find that they're not genetically mapped. They're not. And he infers from that it's not a hospital transmission. Almost certainly wrong, right?
Mhm.
Because that's where she got it. She got it at this hospital, so it's probably her. And they are the same, but somehow they're not genetically equivalent, right? They're different morphotypes.
You're just looking for a reason why it be genetic diversity
Yeah,
in the hospital.
yeah. It seems to me that it's just, I don't know if it's the
We need to think
Genetic-
of great biological interpretation
Yeah.
of this result.
So,
This is the
but
different
in
part.
your dynamic, these guys, so at the leading edge of as they're spreading, they're mutating into all the other
Yeah.
kinds as well, right? But so there's a load. There's a genetic,
But there's a front wave,
Is it-
still mostly consistent.
Yeah.
right?
So
That's right.
So I don't
Small
have any
mutation,
of the actual the zoomed in shots of the
Yeah.
of the very front, but I've got some of the simulations to show as well. But,
disease transmission is the perfect example of, right near the zero unstable equilibrium, right?
Yeah.
Because it's
Yeah, it's very low. Linear
Very
is
low.
good. Linear is good for disease transmission. Linear is good for.
So there's always in those models. There's always a trade-off between virulence and transmissibility.
Exactly. That's what they discuss.
It's
This
a
is like
functional
you
trade-off.
ask the Dykaiser, he'll tell you that this is either this
so
or that.
like the heterozygosity, it's not
Yeah,
that at all, right?
Yeah, and that's what I'm saying is they all say it. If you say virulence and the transmission of the diseases, they would say all these guys are dichotomous. They're either one or another, and then they have a deep philosophy of why.
Right.
But the reason may simply be that that's what reached us.
Right.
The way they reach us when we look at them, they are already we are seeing the front of the wave.
Right.
And that when they reach us, they have to be like that.
That's,
And that's a very big.
but that's an interesting thing because they only arrive at that through modeling, right? That's the only time when you have an interesting dynamic. So I think it may be highly equivalent to what you're doing. It's not like they went to empirical cases and said, "Gee, we always find this trade-off between virulence and transmission."
I think
I don't think that's the case at
They
all.
don't, but I think that's what they say.
I think when you run a
Biologists say
model, you only get stability. in the model.
But his results are actually completely different from that, because you're talking about like one trade off in one direction only generally.
No.
He actually says you
There's
need
two
both of
things to
them,
trade off.
and they are collaborating in some sense to
In
make the
some
invasion.
sense, that they're the winners. There are a
Right.
couple of winners that
And these two morphs,
that are inversed substantially in D and R. That's winners, right? So if by some reason we only accessing, like in natural selection, we only accessing what's left, and we don't see the process, but we see the result. If in diseases we see, for instance, the front wave of the long-going, very low-level process, that's linearization is fine assumption for it because it's very low frequency, right? Low disease rate. And then we might predict that we're going to see virulence and transmissibility reverse as a reverse trait without
Oh, that's in the evolution.
Giving-
Sorry, it's in an evolving disease.
as an evolving,
Right.
not as
So that's
the,
why. That's
not
why
the
you get
physiological reason that it has to be because of energy use, but as a that.
but
reason.
that's the long
It's to
term.
reproduce the observed pattern that when a disease arrives, it's highly virulent, it kills its host. But then over course,
Of
as it runs its
evolution.
course and hosts become rarer or something, it evolves towards higher transmission rate, better at finding hosts, but doesn't kill them.
And lower pathogenicity.
So in a sense, it's when it's in the explosive spread, it's I just
But the
don't-
both morphs are present. That's the thing.
Do you have
yeah.
40 more?
All these
Oh, actually, I can
But the
look.
both morphs are present.
Do you have 40 more
I
slides?
really like
got a few more slides, yeah.
to
But
It's
there-
basically just to show the.
that may be
You have
With
20
the
more
selection
slides.
inside
Yeah.
the body.
He has 20 more
Yeah,
slides,
You
so
get
we should probably
low
let him
virulence
finish.
to evolve inside the body because the highly virulent one wins.
Yes, but no, this is a spread across people.
That's
It's
right.
not
That's
actually
right.
20. It's more like 50. He has 15 more slides.
Okay,
Let's
Let-
okay, you
let's
have,
go. I'm very interested.
you
I
have
think
3.5 minutes.
That's okay.
That's right.
No, we have time. I like to listen to it.
Yeah. So we have a mathematical prediction for the invasion speed. Analytically, we see that it's valid. But the important point here is that a linear prediction doesn't imply a nonlinear speed. That's not inclined to be true. So what we check is whether or not the linear prediction is matched by the nonlinear simulation result. So we want to see what happens essentially.
With quadratic terms. With
Yeah.
quadratic terms in ends.
Yeah. So for our numerical simulations, here's the equations again. We just discretize them in a second order and time and space finite difference method, commonly known as Crank-Nicholson. So for a competition, we just set this as 1 over the carrying capacity, which essentially sets competition neutral. We use the mu 0.001 and our time steps. So our time step and our spatial step are the same, and the 0.001. So we use the 12,000 sort of size, but you split that. For the spatial step, we split.
L is space.
Yeah, so it's just like a grid, and then you discretize this up.
Okay.
And then time over 3,000.
Does it get to the end of 12,000 and
No,
3,000?
it's deliberately done that way because
You don't
Right.
want to go to it.
you don't want to go to the end. It's,
You want to see.
theoretically, it's an infinite landscape
Yeah.
with
Right.
one half occupied, one half not.
Okay.
So for our parameter values to hit home the point that it's only 2 that dictate the speed, we use 10 phenotypes with ascending order and dispersal coefficient and descending order and reproduction coefficient. So basically it's a sense of R equals 1 over D is whatever is the sort of relationship you have. There's no sort of biological founding for it, it's just values that we wanted to check to make sure that the analytics match the simulations.
I'm confused. Shouldn't you have another wing above of like 10 more phenotypes symmetrically going the other way to make reproduction biggest while dispersal is smallest?
It's just a scale
That's it.
question. How you scale
Well,
it.
but
Yeah. So this is smallest dispersal, largest reproduction. Largest dispersal, smallest reproduction.
I mean, if you add a number to the reproduction coefficient, then they'll intersect.
these are coefficients. They matter. Their magnitudes matter, don't they?
Get it? Yeah. Well, for the sake of predicting speed, yeah.
And so why isn't there a one that's dispersal
Go,
10th, one,
fractional
Well,
yeah,
because-
1/10
if-
dispersal coefficient and 10 reproduction coefficient?
It's just a scale sort of thing. It's just they're just different. So it's
I reserve the right to be mad
Okay.
later.
yeah. I can show you the graph of which it falls off.
Okay.
So here's what we found in our simulation results. It's difficult to see here, but this top one, this eye, as you see, it's the same type of shape that we've seen in the Elliott and Cornell paper. But this top one contains all 10 phenotypes. So what we have is phenotype 1, which is some peak at the front, and the rest of them meet down here. This one particular slide is to show that this is a 10 phenotype case, this is a 3 phenotype case, and this is a 2 phenotype case. The 2 phenotype case is the one which gives us the invasion speed. But as you can see, in 10 phenotypes and 3 phenotypes, it's still traveling at the same speed because this, along the x-axis, is still the same space. They're taken at the exact same time shocks. And here's just as well for this 4 and 5 is to show that both phenotypes, which in isolation travel much slower than this combination. For example, the D and the R values are picked in such a way that the monomorphic speeds are all the same. So this is just so we can show that they travel at the same speed.
Right, because DR is always 1.
Yeah. So here we have our speeds predicted analytically. So for phenotype 1 and 10, the analytic predicted speed is this. And here we have the monomorphic speed predicted at 2. And from our simulations, this is our...
Close.
Yeah, we're close. We're close within the realms of the error of this finite difference method. We still fall within the error. As you see, it gets where we're pretty close to the speed. So it gives us more weight to say that, yes, it suggests that the nonlinear system travels at the same speed as the linear, but we couldn't show that analytically. We didn't find the linear determines the condition. So what we found from these, if you remember from that last table, was that it was the most dispersive and the most fecundant, which were giving you the speed 1 in 10. So phenotype 10 was a greater disperser poorer reproducer. Phenotype 1 was the better reproducer, poorest disperser. So do we always see that that the population is driven by the extremes? This is one of the questions we wanted to know, because sort of heuristically in your head it kind of makes sense. But the maths actually tells us this isn't necessarily the case. So we just chose a full phenotype example just to make use of this. So epsilon here is a small parameter, and it's the same in x is a non-small parameter. So here we set up phenotype 1, which is a poor disperser, so it's got a low value. And then we have a reproduction coefficient plus this small value, which says it's the greatest sort of reproducer. And then vice versa for phenotype 2. And then we introduce phenotypes 3 and 4, which are they'll just perturb ever so slightly around this constant value x. So it's close to the same, it's close to being a good reproducer, but it's just a poorer disperser and the same again. So one of the first things we've done was we just checked this using Taylor expansions. Here are the expansions if you're interested in them. Here's because we expand around this condition for these sort of values. But the most important point here is this column and this column. So this column contains the speed, and this column contains whether or not those two simultaneous conditions that we found for anomalous invasion speeds are satisfied. And we found that the extreme case, yeah, we still have it, and we don't have it for the rest, so it's not satisfied. But
you go to infinite.
Yeah, so you don't see these speeds because this condition isn't satisfied. Because the condition isn't satisfied, you don't see these anomalous invasion speeds.
It's trying to be infinite, but it can't.
It can. This is just what would happen if you inserted the values into the relation for the polymorphic speed. So they'll travel at the Fisher speed rather than this, if they were in isolation.
Right.
But what we find here is that the 3 and 4, this introduced phenotype, where they're fairly close together, that it is also satisfied, and it's also faster than the extreme case. So we just translate this into a numerical example, which is probably easier to see. And these are just some of the values for it. Again, is the condition satisfied? Is it not? Here we see that, again, 3 and 4 travels faster than 1 and 2.
Can you go back to your setup table with just the plus and minus
Which one?
epsilon? So it doesn't look very special in
No,
the setup. Yeah.
no. It's much easier to see here.
Yeah.
Because it's essentially 0.1 is epsilon and 0.9 is x. So it was just set up in such a way to illustrate the point.
Mm-hmm.
And again, the same thing we see is that this time it's just done numerically.
So it's not the case that we'd expect to see
The extremes.
widely divergent things.
Yeah.
They're actually
Both kind, dispersal and reproducer.
Yeah.
as similar as
Yeah, but they still have to be different because by a certain value. Because if you have one good disperser and one good reproducer, it just dominates. It just invades at the Fisher speed as this one phenotype. So long as you have this diversity between reproduction and dispersal, then you can see this behavior. But here's some more simulations that we have for this exact sort of case. So here's that whole 4 phenotype population invading at such a speed, and here's phenotypes 3 and 4, which gave us a faster speed, invading faster than phenotypes 1 and 2, which were the extreme phenotypes. So this is just to show that yes, the greatest disperser and the greatest reproducer do not necessarily have to are not necessarily at the ones who who predict the speed, who dictate the speed of invasion. That's to show that isn't necessarily true. So the conclusions that we found, some slides haven't been included, was that this, as again to reiterate, is that the speed of invasion for these highly polymorphic populations was determined by at most 2 constituent phenotypes, and that these need not be the most dispersive or the most fecund. They don't have to be. So our future directions, just as Nick was sort of alluding to there, is what happens if you impose a trade-off on top of this. Would you see constraints on invasion speeds, and will particular forms of trade-offs imply fasting?
What kind of trade?
So this is just that sort of 10 phenotype case. It's just this sort of negative.
But that imposing it means that as an organism, you're either doing this or you're doing that. You can't do both at the same.
Yeah. So it's basically just a curve between dispersal and reproduction. It's something we can impose as many theoretical ones on as we like. It doesn't matter. It's just a case of, do the values fall on such a curve? But what's more interesting to find is if you have, say, an empirically known trade-off to impose this, would you still see this type of behavior?
I see.
That's the sort of direction that we're trying to go on.
That's playing along with what biologists said
Yeah.
about the trade-off. I thought he would be much more evolutionary by saying that trade-off is fake.
Yeah.
Well, but
what
no,
you created-
he dashed.
The trade-off
he
is
dashed all
a
my
necessary
excitement there.
consequence of what happens.
But the vanguard isn't made up of this set of extremes. The thing that's moving the fastest it hardly looks like there's anything like a trade-off there. There was very small.
Yeah, the
difference
fastest
between-
you
That was
said
the
was
previous
8 and 9.
I thought it
instead
was
of
on
0.8,
crazy
0.9.
pills.
Yeah, and
The
that
fastest.
Yeah,
They were not different. They were not disparate.
yeah, in
Yeah,
this case.
the
Can you go to the previous slide?
Right,
I
so-
thought I just completely
this is
misunderstood
the
everything.
least-
Then I misunderstood.
these two are
These
the
two
least
were the
extremely
fastest.
different, and
Yeah.
this is the fastest one, right?
He said they don't have to be, but they can be.
Yeah, they don't have to be, but they can be.
The fastest disperser and reproducer can be leading the
Yeah,
way.
they can be, but provided, from what we've seen, provided that they met these two conditions.
Right. So I made the mistake of I focused on your conditions. Can you go back to the slide that shows the
So
speed?
CP isn't actually the realized speed. It's what is CP?
It's the polymorphic speed for each pair of phenotypes.
So
Yes.
But that's
I
inequality.
don't understand this at all.
But can you go back to the
I didn't want to slow
formula
you
for
up,
CP?
so I
Yeah.
just
I know it's
delayed
really
it.
bad. I know this is
Oh, there we go.
not right. So if it was just the numerator, then we would be expecting. Actually, if it was just a numerator, it explains why you're not guaranteed to get a high speed from having extreme values. If RL is huge and DM is really small, you get a middling number.
Yeah.
And vice versa. You need that difference to be large in the numerator.
So every time we ran this, every simulation we ever ran, if there were more phenotypes which satisfy this condition, which, for example, that 1 to 10 numbering, all of them satisfy this condition. However, whenever we ran them, whichever one satisfied the condition, it was always the fastest which emerged from the simulations.
Mm-hmm.
Always the fastest speed. And
Sorry, what was the fastest?
the speed which the invasion traveled at, always traveled at the fastest speed. Now
The condition is greater than 2 for this.
yeah, provided
Basically,
they
But
provided
3 and 4 are also
An
greater than
efficient
2.
algorithm.
Yeah.
3 and 4
finding out
as well
fastest
as
yeah,
at first, right? In
Yeah.
fact, 3 and 4 are. So there are 2 potential
Right,
pairs
so-
that
Yeah.
satisfy.
I thought that was
So
the
the bigger the
point.
difference, in fact, we know that these need to be in opposite directions.
Yeah.
But the bigger the difference between the parameters, the slower this gets.
Yeah.
so there's and within Vansalus's paper it says because you've got lots of different K values that come out of this, it's the smallest one which should travel at the fastest speed. You should always see this emerge in the system if you have several, which is my justification on it. Stephen doesn't want to jump on it because we've not done the calculations ourselves for it. But that's why we say mathematically, so long as the conditions are satisfied, the system will always try and go at the fastest speed possible, even if there are other speeds possible. So for example, in this case,
But it doesn't make sense to say that
yeah,
they'll go at other
They both
speeds
do.
because
But I
they'll
still
all go at
couldn't
all
fully
speeds. And
understand
what
that.
you see
In
is
this
the
case,
fastest.
this guy's at 10
well, no,
points.
that's not true.
Yeah, on the
the
line
full
one,
population.
this sums at 10.1. Of course, they are greater than 2. 10 is greater than
Yeah.
satisfied. And this is 2.01. That's also greater than
Yeah.
satisfied. And as they are satisfied, which if I have a mixture of all the phenotypes, all 4, which one is going to win? The 1, 2, or 3, 4?
3, 4.
3, 4 is going to win, right?
Why?
Always.
What?
It
So
gets
I don't
1.7.
understand. 2 is
It
bigger
has
than
the
1.
highest speed that also satisfies the condition.
So these are not really the realized speeds then, or the projected speeds. The
They are.
CP. Well, except that 2 is bigger than 1. So
But it doesn't meet the condition, so it doesn't.
I know that's what I'm saying. So it doesn't
So
travel
these
at
don't
2.
exist at 2.7.
So
It's
those,
really
Yeah,
should
they
be.
don't
It really
exist.
should be a
First and
bar
last
there,
number
right?
exists.
Yeah.
so those things that satisfy the condition.
Yeah.
This is
If you don't satisfy the condition, you don't get this.
You said that they go at Fisher speed.
Yeah.
So what's
which is
Fisher
much
speed?
slower.
Slow.
Like what?
That's a
Numerical.
single species speed.
So because I'm confused because those 2.68 is bigger than 1.1.
2 times the square root of dr. So
Yeah.
2 times the square root of
here,
q.
it'd be 0.01. 2 times the square root of 0.01.
Just under 2.
Okay, so there's really.
the Fisher one is without polymorphism, right? That's like a single species,
Yes.
single
Yeah.
form, single morph.
So the realized speed is another column.
Well, we'll think about it.
Yeah.
But
That's
my
the speed it
favorite would be
travels
to turn around biologists and reinterpret everything.
Well, it's because he was very excited when he explained heterosis.
Explain something. You know, it's just like I
Shows
was trying to
really
explain why
artifactual.
heterozygotes are superior. I said because that's the only one you could see. You can't see any other. The ones that are not superior.
They're
gone.
not superior.
Already gone, right? Superior. And so there's nothing good about being heterozygous. In fact, majority of loci in nation species are monomorphic. Because heterozygotes are intermediate most of the time, and they're gone. We don't see them. But this minority that has superior heterozygotes is the only one we see. And then we have hybrid vigor and all these biological things. They're simply the only thing we could see.
Yeah.
We just can't see any other. So there's nothing good. It's just what we can see.
For decades.
And so what I was just saying, if I turn that to your subject, I would just say, can't I prove that this so-called trade-off between dispersing and reproduction is the only thing you can see? It's not like, it's just,
Yeah.
it's selected, whatever. It's just what happens. You can't see any other. And so you don't need to add,
So it's not that there
you
is
don't
a
need to
trade-off.
add physiological
you don't need
explanation.
energetics. You don't need.
No, you don't need
competitive
like
ability,
heterozygote
anything.
superiority had stories.
Yeah,
What
they
kind of
try to
dark? The stories
explain
are like,
why
well,
heterozygotes
when you
work
have 2
or
alleles
that.
rather than 1 in variable environments, sometimes you kind of put one cheek, the other time the other cheek, and in the variable environment you're going to be better off having 2 different alleles
All of
than
that's
2
bullshit.
of the same. That's all garbage. It is just simply when you have heterozygotes accidentally superior, then you're going to see them. All the rest are gone. What you're saying is, if they are not disparate,
Mhm.
you're just not going to see them. They're gone.
They didn't,
You only see those.
they didn't invade.
They just are not on the front. And what we see
Yeah,
in
not on the
biology
front.
is front. Let's say in biology we see fronts. In disease spread we see fronts of the wave. And so we guarantee that viral diseases have to be either virulent or dispersant, one or the other. But their trade-off is given by this what you just discovered,
In a
and
sense,
not
it's
biologically explained by some physiological trade-off. So I didn't like your last trade-off story because you're trying to play along with biologists and impose what they say. Don't impose it. Explain what they find by your math. The math is fundamental. You tell them you don't need to explain this trade-off. Trade-off is coming out by itself from nothing, from math, from actually what happens. And you're just overthinking it by presenting physiological reasons for trade-offs. Well, I have the reason why trade-offs can be the only thing you can
Mathematicians
see.
have to crush the biologists.
So basically it is like the Armenian view of you could only see what's left after selection.
No, I would actually say there could still be an evolution of a trade-off. What I like about it is that it's not driven by constraint. I can't do 2 things.
Yeah, like this. Yes,
it's not really a
exactly.
trade-off.
Yeah.
The trade-off
Yeah.
is when I cannot possibly optimize 2 characters. In this case, it's
You can't.
evolutionary of a functional relationship between 2 things
Yeah.
because
You could
There
say,
is
I
a-
explain this
there's a
relationship.
set
When the
of-
biologists
In fact,
come, they have to see
Isn't
this
there
way
the anomaly
because
of
of
the
my
super
result.
trend?
Yeah.
You need to explain biology
the super
as,
trend.
as what is left
Isn't that
after
the-
all the rest is gone.
You're
Like
explaining why
Darwin
they don't
explained
exist.
natural selection.
Right.
But you explain this, not impose.
Generalist is best at everything.
Yeah, you be a star.
This is
you
the-
explain this.
Jeff Levinson talks about the anomaly of the supertramp. You know, why there aren't these supertramps around. And I think he calls them supertramps. They're the guys who disperse and reproduce really good, but good at the same time. The best, right? Because you can do it this way, you can do that. But the supertramp, the one that does best of both, isn't the one that wins.
Right.
And so Levinson sort of, I mean, I remember him discussing this years ago. He said this is a big mystery why this is the case.
See, biologists, seriously thinking biologists would not. Either they say it's a trade-off that's built in from physiology. You can't do both, but then maybe you explain it. That's what I'm saying. Is don't impose it. Explain it.
So it just really does take the form of the curve. I mean, if the curve takes this sort of
you explain that curve.
That's the curve that explains the best differences between.
Right, sure. But you explain the curve, and then you just put everything upside down. Put everything upside down, and tell them that maybe you don't need to explain trade-off as physiological process. Trade-offs happen because of your argument.
They seem to happen.
Yeah, they seem to happen because of your argument, and then they appear, and people will explain them by. But you're really there because of that. Like, I mean, just like natural selection resulted in few genotypes and the rest is gone, and it's not.
Do you still have 15 more slides?
That's what's left.
no, it's basically.
I like it very much. If you put it upside down, you'd have a great. You put everything interpretation.
If you just put not
put interpretation upside down.
I think that the most important.
Stand up like this, interpret it as an explanation of what biologists see, and they.
No, the most important next step is to make it a simple diploid model where I guess unfortunately maybe you need two loci or something. Is that the word? You think it through, but there's a locus for how reproductive you are and a locus for how dispersing you are. If you put them in the same locus and it's an either or, then you've already made the trade-off. So make it so you could have things that are fantastic reproducers and movers. But then only because now you have and you can have allelic mutations, right? But it solves this problem of how to do mutation and also what kind of offspring I have, right? We accept Mendelian segregation and all that stuff. So the things at the leading edge would be creating things that are faster and slower than them, and it'd be very interesting to see, what you.
Yeah, that's one of our sort of targets on the hit list.
But even without, no, this would be wonderful. What you said, great. Well, in your field of study, like, don't you have dispersers, guys? Insects in the field of.
We're just,
reproducers. I mean, don't you have?
For part of the Monsanto project, what they want is there's a fraction of females that go up high and take off, and they'll say, they're heavier. So actually, the opposite is usual. They have more reserves. They have more eggs, and they're going to go farther. But they immediately want to start describing as distinct form.
Right away.
And there being inherent trade-offs, all this kind of stuff.
No, when people talking about trade-offs, I immediately I really
should
like
be
suspicious about trade-off as a fundamental. You explain the trade-off by what you found, rather than, and that would turn everything just like.
Yeah. Yeah, I agree.
Yeah, I mean that will be just strong. It's a discovery, kind of like some scientific discovery based on mathematics.
Right.
Very exciting.
Yeah, I think a very exciting thing can come on. So I would reinterpret it right now, even before you do the other work.
All of those central questions: why is there so much heterozygosity in nature? Why are there so many species? Any kind of why is there so much diversity question? What has previously been answered by either everybody's a specialist on something different,
right?
Yeah.
Or, so the world is heterogeneous,
right?
Or diversity is a result of you can't optimize. I mean, it's the same thing. You can't optimize on everything, so that's trade-offs. Or somehow there's cooperation or something that makes diversity better than some part. But you've come up with a non-cooperative system where
that
diversity gives the best performance.
Yeah.
That's a
big
certain
That's very, very
and I think it has medical
if
applications
it's reinterpreted biologically upside down.
And I think it has medical applications too. It's,
And medical.
It's fundable.
With virulence,
It's fundable.
And,
with an age.
spread.
Absolutely.
virulence and spread. Yeah.
I actually, I laughed when you said military applications, but I think you could totally.
Oh, absolutely.
To,
Oh, hell yes.
Invasion planners.
Hell
Like,
yes.
What? I want to put slow things with fast things.
Well, they don't reproduce right there. But
No,
They just swap toys.
They have to be able to mutate into different.
do they?
sorts of
Is
things.
reproduction essential to this?
yeah,
Uh,
it's exponential. It's
Well,
it's
but-
exponential.
You have to come up with a.
When you conquer lands, you've
Yeah,
essentially
it also no,
reproduced.
you know what the other thing. If you take, there's another interesting field of application. It's completely opposite, I think. The other way, linear approximation is good around zero. It's all pharmaceuticals, but they are going out of your body with certain exponential rates. So exponents are declining. So you get a drug, and 15 hours later you don't have a drug. It's all in the urine. Different drug has different exponential decline.
Right.
Phase. It may be that. And they're exponential, but declining, not increasing. Maybe there is something about interaction of drugs or something, which one is, I don't know, slow getting out, the other is fast getting out. And there's something inverse about negative exponents as opposed to positive exponents of growth.
There's no reproduction there either.
There's no reduction, but it's exponential, I'm just saying, because it is dying out exponentially. It's a very good approximation for drugs. Disappearance from the body exponentially is perfect because it's linear. It's linearization because it's all very low.
Pharmacokinetics.
Pharmacokinetics is all
Very
linear
elaborate.
and it's good approximation. Linearity is good in pharmacokinetics, but it's different. It's also exponential but declining and not increasing. We need to think about it a little bit. But if there's something very interesting that one can do on pharmacological interpretations of exponential but declining things. Maybe. I was just thinking where else.
The military thing, if you think of invading a country as a combination of capturing and holding land, right? And army engineers are for holding. They're like the reproductive part. You have some land and you put roads on it and defenses, and then there's a force that captures the land itself, which involves
Frontier.
right? Those are the
Paratroopers.
expanders. So there's some optimal combination of engineers and combat forces.
There you go.
Like more global instability.
Okay, guys.
I have to go. I'm sorry.
That's very,
Very
that was
interesting.
I think it's a great, interesting result. Not, the people like that, not for nothing.
Yeah.
They understood it. But I think that biological interpretation needs to be more evolutionary, and you'll get more brownie points for that.
Now, you're not allowed to advance your thesis in any way while working here. That was an interesting part of the fine print. So I guess you shouldn't acknowledge this.
Is that really part of the
He's
plan?
not allowed. No, the
Yeah.
rules of university, whatever he done in these 3 months is not part of his thesis.
Yeah, I couldn't
Oh,
include it.
let's
Well,
stop
all
sharing.
Let's stop right there.
So,
We
so now
can't,
that we've recorded that
he's
entire
not allowed
conversation,
to. He's not
No, it
allowed.
just
But
means
ideas are
you-
free.
It
You
just
could
means you
use the
can't
idea.
submit a chapter for your thesis
Yeah,
based on what you did here.
Yeah, that's true. I could use some
That's
dispersal
also-
and stuff. Then.
That's
mean,
also
We could do
bullshit.
that.
That's
We have to
crazy
erase his
talk.
memory before he leaves.
Yeah.
That was the deal why they give me the money. So
To get experience
yeah, outside of academia. So
outside.
that was the whole kicker.
Well, why do it before you're done then?
Well, the idea was that if people would go and do it, they would try and do something because you get a funding extension for it. So the idea was they wanted to stop people thinking, oh, I'll just go and work in something that I'm used to, just trading one comfort for another. Rather
I
than,
see.
So
Then really
sort of-
expand your
yeah,
horizons.
and so
Nick, give him some
right.
something to learn.
That's why I'm
new
having Vinny
language.
paint my house this weekend.
Yeah, I already invited him
Wax
for
on,
gardening,
wax
but
off.
he doesn't want that. Yeah, so no, I think give him some programming work on the new software.
Yeah.
That he cannot put on the thesis, which is good.
Well, yeah. We got.
Well, I think it's great. Great.
yeah, that's one of our next stages is to
Yeah, and next stage is do the deploy it maybe.
Yeah.
We'll say what Nick said like that. But I think even without it, this is great.
yeah.
But even without it, I think you should reinterpret it. I should convince your teacher about that.
Yeah.
We should have a Skype with him.
Yeah,
You
well,
and I,
well,
let's talk to him
yeah.
on the Skype one day.
yeah, because I'm trying to speak with him just now so he can give me. So we've done the nearest neighbor stuff.
Yeah.
Run the simulations. At first, it seemed as though the whole calculation was going to break down, and it was all rubbish because you didn't find the two at the front. You just found this sort of ladder because you see that trumpet-like shape. It starts becoming laddered when you do that. So
Oh, ladder, one after another, not the pair.
yeah, with the pair at the front. So this is what we found. When we looked at the very low density. If you see the trumpet shape, yeah, it's fine. That's just what it looks like after. But we're talking right in the front. It was small, and then there was sort of a kind of change. But Stephen was like, the whole result's garbage because it doesn't show what we should expect to show.
Why? It still sounds like you're trying to train it too much.
Yeah.
What if you just chose small random perturbations to the value? So I'm going to have kids who are just slightly different from me.
Yeah, well, this is what we do.
Yeah,
When we make mutations.
We are not
small,
uploading.
yeah.
Let's upload
Yeah.
the speaker. Okay.
Nice.
We forgot.
Upload.
Okay.
When
We
track
already
mutations,
uploaded.
Yeah, we
small,
already
small,
uploaded.
All right. This is
For some
great.
reason,
We
I
didn't
forgot
applaud the
to do
speaker
it.
on the upload though.
He ran it with a smaller order, and yeah, we still get it. You actually find the disperser. Out of this pair, it's a disperser who leads and then eventually a little bit back, this reproducer. So they're both kind of at the front, if that makes
Oh,
sense.
okay.
So he was
It's
able
almost
to.
like you're picking up some spatial resolution.
Yeah, yeah, that was it. It was
Right.
It was just a small
Yeah,
mutation.
if one of your Skypes